This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, so can you read this? Is this size large enough? Okay. All right, so let's get started. Today is the second last lecture of the potential flow part. And before we start talking about potential flow again, I would like to make a few announcements. So first of all, on Monday, I got some students asking me if I have any spare copies of the summary sheet. And unfortunately, I don't have any of them. So if you want to have the summary sheet, please email Leon to set a time so we can collect the sheet from him. And for the last lecture we're going to have tomorrow, we are going to have a revision of the whole potential flow part. And is there any particular topic you want me to cover? Or the what? Previous. Okay, well, that seems like a lot. So what I have prepared so far is just a few examples from the past exams. I'll probably show the duration, show the working of one or two of the past exam questions, just for you to get a feel of how it looks like. And I'm not sure what else you want to know from the revision session. Yeah. How to draw streamlines. Yeah, okay, I'll include a question of that. Okay. I'll choose a difficult one for you. Anything else? Yeah. Oh, okay. And from next week, we're going to have the compressible flow lectures. And there'll be a different lecturer, Professor Gary Brown. Probably you have, Leon has already introduced him to you. So Professor Brown really, I talked to him yesterday, and he said he really prefers to write on the whiteboard, although we don't have a whiteboard here. So I'm not sure what he's going to do in this room. But just to let you know, if he shows the derivation on a whiteboard, that's not going to be recorded by the lecture capture system. So I would highly recommend that you should come and sit in the lecture halls, okay? Otherwise, you're going to miss a lot of information from his lectures. And that's about it for the announcement. And for the lecture today, I think I'm going to start with showing you, I'm going to go through the Coulter condition again. And then I'll show you the derivation on the document camera. So I think it's a better way to follow. Okay. So we actually have covered all of this in the lectures on Monday. So let me remind you of the Joukowsky transform where we have been looking at. The transformation goes like this. Zj, which is the coordinate in the new plane, is equal to z plus c squared divided by z. This is the transformation we have been looking at. Okay, it can transform a circle from the original plane to an airfoil or to an ellipse in the transformed plane. And there are some properties of this transformation. So we can, if we calculate the derivative of this one, we differentiate that. Dzj, dz is 1 minus c squared, z squared, right? And we can see that at the two critical points, which z equals to plus or minus c, that is basically, if I draw the Joukowsky circle on the plane, these two critical points are just here, and here, these 2 points on the real axis. So at these 2 points, the derivative goes to 0, which means that if we have a smooth curve in the original plane, that will be transformed into a cusp in the transformed plane. And that point corresponds to the trailing edge of our airfoil in the new plane. So one thing that comes directly out of this critical point is when we want to calculate the velocity in the transformed plane. We have the velocity magnitude, okay, Vj equals to the velocity magnitude in the original plane divided by this multiplying factor, dzj, dz, the modulus of this. Okay, and so if we take a closer look at this term here, we can see that at the two critical points, this magnitude will go to 0, which means Vj will go to infinity, right? If this V is non-zero. So here comes the Kodak condition. What we can do to stop Vj from going to infinity is that we want to adjust the original flow, so there's a stagnation point at the critical point, which means that we need V equals to 0 to stop Vj from going to infinity at those points. So with this in mind, we can look at how the flow looks like for symmetric airfoil, and then later on we can look at the cambered airfoil. So let me give you an example of the symmetric airfoil. This is the original plane, X and Y. And then I'll sketch the Joukowsky circle with red color. This is my Joukowsky circle, and the radius is C. The center of the circle is at the origin of the coordinate. And then I need another circle in the original plane to perform the transformation. So I have something like this. Okay, so this is the circle I want to transform to the new plane. The center of this circle is here. Okay, see, it's shifted from the origin of the coordinate by an amount, I'm going to call it x naught. And the radius of this circle is A. So what we can see here is that the blue circle touches the red circle at this point. this is one of the two critical points. And this is the point that is going to be transformed into the trailing edge of the airfoil. And then the Bottomley shift of this blue circle is just x naught, right? X naught is equal to A, the big radius minus the radius of the Joukowsky circle. So this is the Bottomley shift. And we can sketch the incoming flow on this graph as well. We have U infinity coming from right to the left. Okay, so this is the case of a symmetric airfoil, and in this configuration, the angle of attack is 0 because the incoming flow is just aligned with the x-axis. Okay, any questions so far? All right. So this case should be straightforward for us. When we have the incoming flow going this way, we can see that the flow around the cylinder will give us two stagnation points. One is here, and the other one is here, which sits right on top of the critical point. So we don't have the problem of Vj going to infinity at this point. So far, so good. And what if we consider the angle of attack of this flow? So imagine we, instead of, for U infinity, instead of coming from right to the left, we consider an angle that goes, U infinity goes this way. So this is the new direction of U infinity, okay? And I'm going to call this angle alpha. This is the angle of attack. So in this case, the two stagnation points will be moved to here and here, right? But we want to have a stagnation point at this critical point. So what we can do is to add a circulation to the flow around the cylinder to move this stagnation point to this place, right? So we need to add a circulation, gamma, and so we can move this stagnation point to this place. So I'm going to call this angle theta. So we can see that from this sketch, we can see the relation between theta and alpha is theta plus alpha equals to 0. And then if you still remember the relation between theta and gamma from a few lectures ago, you can write theta equals to arc sine minus gamma divided by 4 pi U infinity times A. Right? And we can later on rearrange this equation and solve gamma from this relation. Any questions? Okay, so this is the case of a symmetric airfoil. And we can add a little bit more to this by considering a cambered airfoil. So let me keep it here and I'll sketch it again. It's the same Joukowsky circle. So what's the difference between a symmetric airfoil and a cambered airfoil? I can't hear you. Yeah, that's correct. So instead of shifting this blue circle along the x-axis, now I can shift it along the y-axis as well. So, for example, I can draw my blue circle here. This is the center of my blue circle. and then it will be shifted like this. Well, this is not very centered, but you know what I mean. This is the circle with the radius of A, and then now I have two shifts. I have one shift along the y direction and the shift along the x direction. And the blue, again, just like the previous case, the blue circle touches the red circle at a critical point as well. So the first question I wanted to ask is, what is the shift x naught that I need? Usually this y naught is given to you. Y naught is related to the camber you're after. So y naught is usually given. But how can we solve x naught from this case? So one way to do this is we can look at this triangle from this point. If I connect this with the center of the big circle. So let's consider this triangle in magenta color. You can see that this edge, the length of this is A, and the length of this is the radius of the Joukowsky circle plus x naught. So it's C plus x naught, and this one is just y naught. So we can say that from the Pythagoras theory, A squared, this length, is equal to y naught squared plus x naught plus c squared. And the only unknown in this is just x naught. So we can rearrange terms and solve for x naught, which is a squared minus y naught squared minus c. Okay, so this is the Bartley shift we need for to get a cambered airfoil. Okay, and then the next thing is we want to consider the flow. Let's consider the zero angle attack. So we have the flow going from right to the left. And in this case, the stagnation point of this flow around this cylinder should be here. If I draw a horizontal line that passes through the center of the circle, this point and this point, these two should be the stagnation point, right? And we can see the difference between the cambered case and the symmetric airfoil case, that is at zero angle of attack. In the symmetrical airfoil, we have a stagnation point already at a critical point. But when we have the cambered airfoil, it's not at this point. Okay, which means that if we have a cambered airfoil, even if there's no angle of attack, we can still have lift on the airfoil. But so for this case, we want to move the stagnation point to the critical point by again we want to add the circulation. So I'm going to call this angle beta. It's getting a bit crowded. So this angle beta is arc sine. This length is y naught divided by a, the radius. So we need to move the stagnation point, this one, by this much, so it can go back to the critical point. So in this case, we'll have theta plus beta equals to 0, and theta is that angle related to the circulation. Okay, this is the case of zero angle of attack. So what if we rotate the incoming flow just like we did previously? We can consider this. U infinity is coming along this direction now. And again, I'm going to call this angle alpha, the angle of attack. So now the true stagnation point has been relocated to these two places, the two green circles. So we want to move this point back to here instead of this point back to here. So this time, since I know this is alpha as well, this relation will just be changed into theta plus alpha plus beta equals to 0. Okay? And then everything else should just follow after that. Any questions? Oh, theta is the, I didn't sketch it here, but I believe theta is from this point to this point, so it's, let me change the color. Theta is this one. So if you still remember those lectures on the flow around the cylinder with the circulation, we usually had a sketch like this. This is a circle, and the flow is coming this way. And we have a circulation, gamma. So the two stagnation points will be moved to here and here. And we define this angle as theta. That's the angle of how much the stagnation point has been moved. Okay, shall I continue? This is just a summary of what we did on Monday. And I think this is probably a more visualized way for you to understand what's been going on with the applying the Coulter condition. Okay, so I'll switch back to the slides. I'll probably just jump to what I want to cover today. Okay, so after all this derivation, now we are able to model the flow over an airfoil, and we can calculate the lift acting on the airfoil. But there are certain limitations of this method. First of all, because it is based on potential flow, so all these limitations or assumptions we have for potential flow will also be applied to this case. So these are some of the assumptions. The flow is assumed to be two-dimensional, and we didn't consider the viscous force, and the flow is assumed to be irrotational and incompressible as well. And so here, another limitation of this method is that it cannot simulate the flow separation. Let me show you an example of the actual flow around the airfoil. The video is not of very good quality, but you can see this as the airfoil gets thicker and thicker. When it gets thicker, the flow separates at the trailing edge, and you can see vortices start forming here. So this is one case where you may expect the flow separation. That is when the airfoil gets too thick, and it applies more disturbance or obstacle or blockage to the flow. So the boundary layer begin to, sorry, I shouldn't have mentioned boundary layer. The flow should, you're going to see some more analysis about boundary layer in advanced fluid dynamics, not here for now. But anyway, all I'm trying to say is that when the airfoil gets thicker and thicker, you usually expect more separation in the end. And another scenario where we have a flow separation is this. This is a change of angle of attack. it starts from 0 degree, and then as the airfoil is tilted more and more, you can see this sheet of fluid got rolled up as well, and vortices started forming. These are the scenarios that cannot be simulated by our potential flow solution. And actually, probably have heard of this already, in aerodynamics, when the angle of attack has increased to a certain value, and this kind of flow separation occurs, the lift is going to drop suddenly, and drag increase a lot. So when it happens in reality, we usually call it stall. And that's really dangerous for aircraft. So to sum it up, there are certain limitations of the method. It cannot simulate flow separation. It also cannot simulate shocks, or any compressible flow-related behavior cannot be captured by this simple model. So this model should only be used for small angle of attack and small thickness to chord ratio, as you have seen in the previous in the two videos, and only for subsonic flow. Back in the old days, when the computational power hasn't been as developed as we have now, people actually use this method to design an aircraft. This is a technical report. I believe Leon found it. It was, I didn't prepare any of this. It was written in 1972, almost a century ago. See the title, Calculation of Potential Flow About Arbitrary Three-Dimensional Lifting Bodies. So they literally just used this potential flow to simulate an actual aircraft. They didn't have the CFD, LES, DNS like we have nowadays. So it's really amazing how they get the aircraft to work. Anyway, I'm not sure what they did exactly, but they can even simulate complicated shapes like the interaction between the wing and fuselage. Okay, so one more thing I added to this lecture is that I have been trying to find the physical explanation of the Kuta condition. You may ask, why is there circulation added to the airfoil? We know that we want to add a circulation so the stagnation point can be moved to the critical point, so we don't have that infinite velocity in the transformed plane. But that's just more like an excuse from the mathematical point of view. So I always wanted to know why there's a circulation physically. What is the physical mechanism behind this? So I find this video. It should be, it should provide an explanation for that. There's a thing called starting vortex. That means if you have an airfoil, okay, it's sitting in a stationary fluid, and then it suddenly starts accelerating and started moving in one direction. So in this process, it will shed a vortex behind it. Let me show you the video first. So we have an airfoil, and then as it starts moving, you can see there's a vortex forming behind it. And just pay attention to the direction of this vortex. Okay, I have a slide for this. So this is just in the opposite direction of what we have been looking at, but I'm sure you can figure this out. Instead of coming from right to left, now the free stream velocity is coming from left to right. The free stream velocity is coming this way, okay? So if we apply the Kuta condition, the circulation should be going this way. So in fact, we have introduced the circulation to the flow field. And before this airfoil starts moving, there's no circulation anywhere in the flow field, right? So what we can see here is that in this vortex behind the airfoil, this starting vortex is rotating in the opposite direction. So in fact, we have two circulations with opposite signs, and they can cancel each other out. So if we consider this volume bounded by this red line, there is zero net circulation inside this volume. And that explains why we should consider there's a circulation around the airfoil, because there's okay, I find this is not very convincing, but there's a vortex of the opposite sign that is shed by the airfoil. And hopefully this can explain why we need why the Coulter condition is physically correct. That explains the origin of this circulation around the airfoil. Does it kind of make sense? Okay, great, thanks. I was trying very hard to find a physical explanation for this. Okay, so that's everything I prepared for this lecture, and it still finished too early than I planned. Yeah, probably that's everything I wanted to cover. Really, that's everything. Okay, so please let me know if you have anything else you want me to cover for the revision session tomorrow. Otherwise, let's end this lecture now. Sorry, just.
So for this one, the very last step is to have the angle of attack. So when we change the angle of the uniform flow, why the shape, therefore it's also changed?
This is just to, in this case, we have the uniform flow coming this way, right?
Yeah.
But we're usually more familiar with the case where the uniform flow is coming this way. So
Yeah.
it's just more like convention, we rotate everything back
Yeah.
so that the uniform flow is coming horizontally.
Okay. So the aircraft is have an angle of attack.
Yeah, that is just a convention.
So when the first step, right, the uniform flow is in this direction, and the first step is to change the angle. So how about the cylinder? The cylinder actually is the source and the sink, right?
Yeah.
So the source and the sink is also changed.
Yeah, everything is changed. Everything is rotated. Let me think. No, wait. Can you repeat the question?
When we change the direction of the uniform flow,
Yeah.
how about the source and sink? Because at first the source and sink is on the axis, right? When we change
Okay,
the
I see what you mean.
Well, we don't care about it.
No, that's changed. That's rotated as well. Otherwise, you won't have a cylinder anymore.
Yeah.
See?
Yeah. The cylinder must,
You have the dipole like this, right?
Yeah.
And uniform flow has to come in this direction, perpendicular to this major axis.
Yeah.
So if you rotate the uniform flow to be like this, and the dipole still remains in the original direction, then it doesn't make sense anymore.
Yeah.
So you have to rotate this to go along this direction.
That means we need to rotate the source and sink.
Yeah.
So for the real aircraft, how to add a vortex, how to add a circulation? Because for this cylinder, right, we need to add a vortex
Yeah.
to make the stagnation point. So how to add it? Or
That's
for the real?
uh, I'm not sure what you mean by the real aircraft.
Yeah.
If you mean the airfoil that is formed by Joukowsky transformation, then the Kodak condition.
Okay. So how to, for example, we want to design an airfoil
Yeah.
to make the stagnation points on these
Okay.
points,
Okay.
right? So that means we need to add first we just design a cylinder and to add a circulation and how to we have the equation to the circulation, right?
Yeah, that's right.
So how to add the circulation for the air?
You mean how to add the circulation to the flow?
Yeah, yeah.
When you do the transformation, you're transforming the whole flow field.
Yeah.
So it's already considered. When you add the circulation to the cylinder, right, and you can calculate the streamline, you can calculate the velocity, everything, and then you transform all of this through the Joukowsky transformation to get an airfoil. So
Okay.
the circulation is already included when you calculate the
It
streamline.
means in the real life, it's already have the circulation around the air.
That's calculated through Kodak condition as well. You can't just go there and measure the circulation. Yeah, I think that's you get that from the calculation. That's my understanding.
Yes. What we learned is very basic, right? It's cannot to design an aircraft after this one.
Yeah, and another way to do this is the panel method, but that's more advanced and it can apply to many other more complicated shapes. That will be covered in advanced fluid dynamics.
Yeah, another question is, so for this one, right, when we change the rotation mapping, right, so the rotating, when the rotating angle is from this direction.
The definition of the positive angle is, I think this is the,
Anti-clockwise?
yeah, that's right, yeah, this is right.
Clockwise, but why, when we change the angle, change the flow, right, actually it's clockwise, so it should be plus I alpha, not minus, because minus alpha is anti-clockwise.
I believe the theta should be the counterclockwise. We change the stagnation point from here to here.
No, I mean when you change the direction of the uniform flow, you change the direction of uniform flow, then we need to mapping from Z to Z1, right? And if we make the uniform flow rotate clockwise,
I think this one should go,
positive, right?
yeah, this one should be positive. If,
Positive?
yeah, if you want to go from this way to rotate it counterclockwise, it should be positive. I noticed that you got this from the lecture slides, right?
Yeah.
Yeah, I noticed that this one is, the sign is wrong.
It's wrong.
Yeah,
So here should be positive.
I think so. If you want it to go that way. Just let me check. It's so easy to get confused.
And sign.
Yeah. I'm never good at this. Yeah, this one, it should be the other way around. It should go down if you want to have a negative sign here.
Okay. Yeah. Thanks.
I have a question about this one.
Yeah, sure.
So, for this question, we know the stagnation point is not the same as the critical point, so we need a vortex.
So, yeah,
So we need a vortex to make them together. But what if the flow is the direction that makes exactly the same stagnation point and the critical point make like this way?
So we don't need the circulation anymore,
So that means
which means that, well, that's possible, right? So when you have a cambered airfoil, if you have a small negative angle of attack, then there's no lift at all
even
for cambered airfoil. You can sketch it this way.
yeah.
So this is the cambered airfoil. If the flow is coming this way, there might be a lift, although it's zero angle of attack. But if the flow is coming this way, there's no lift at all. But on the other hand, for symmetric airfoil, if the flow is coming this way, there's no lift. If the flow is coming this way, it has a negative lift.
Yeah. Okay.
So it's just there's this angle beta that is, it changes the total angle of attack.
Yeah.
I wanted to, but it doesn't let me.